Hi, everyone. Today we are going to talk about conservation of angular momentum. So our first slide just kicks off with an example. When a snowboarder needs more rotation in flight, what do they do to their body? So if you've ever watched the X Games, you have seen a snowboarder go off a ramp and start spinning frantically, trying to get as many rotations in as possible before landing on the ground safely. So uh, when they need to rotate faster or slower, they can actually control their rotation speed. And how do they do that? So first, we can see that they do this by tucking their body into a ball, right? And the tighter the ball, the faster they're going to go. We can see that mathematically using conservation of angular momentum. Okay? If we know that if momentum is conserved, right, that means that the initial momentum is going to equal the final momentum. So if we look at I omega, right, if they just go off the ramp with a normal moment of inertia and they start a turn to get some angular velocity, but then what they're doing is they are decreasing their moment of inertia as small as they can get it so that they can maximize the increase of their angular velocity, right? Because these two have to equal each other, meaning that if you decrease your moment of inertia, your angular velocity has to increase so that you can keep this law of conservation from breaking, right? And in midair, there's very little to cause the law of conservation of energy to start falling out of whack. Air drag doesn't really have that much of an effect on it unless it's a really windy day. So that's how this works. Okay, their angular momentum is conserved, and that allows for a decrease in one to cause an increase in the other. Now, what can we do to test this idea on the spinning wheel of death, and what did you see? So we have this thing in class called the spinning wheel of death. Spinning wheel of death because it's really dangerous to use, and only I, the teacher, and past teachers use it. We don't really let students use it. So I'm going to show you guys what we're talking about here. So this is the spinning wheel of death. It is a wheel that spins. It has relatively no friction, especially when it has weight on it. It actually performs a whole lot better under weight. Right? The duct tape is there just for friction on top. Now, how we can demonstrate this concept is by using this spinning wheel of death. When I set the spinning wheel on the ground and I stand on it, the spinning wheel of death, when I spin myself, okay, I have an initial angular velocity. Now you'll notice as I pull my arms in, now I rotate faster. And now as I pull my arms in tighter, now I'm moving faster. Now as I push my arms out, I am now moving much slower. Same concept, right? Now that's how we can demonstrate this idea on the spinning wheel of death, right? We can show that as I spin and move my arms in and out, that's actually going to change my moment of inertia. And by changing my moment of inertia, I can manipulate my own angular velocity because of the conservation of angular momentum. Now, number 3 asks, what is the fine print of the law of conservation of angular momentum? So the fine print here is that, I'm not going to write that down, that's going to take too long, then you're just watching me write. The law of conservation of momentum is that momentum is conserved if there is no impulse on an object, right? We talked about that when we talked about conservation of momentum earlier, right? Linear momentum is changed if there is impulse. A force acting on an object over any period of time is an impulse. So conservation is conserved if there is no impulse on a system, or if there is no external torque on a system. If there is any unbalanced torque or net torque on a system, that will cause the momentum of the system to change. Now, I can't demonstrate that with the spinning wheel of death because I would need someone else to exert torque on me in order to do that. And I'm doing this alone during COVID. So No demonstration on that one, and I'm dizzy enough from the initial spin. Now, our first problem to test this idea. A courageous / unwise student sits on a freely rotating stool holding a 3-kilogram weight in each hand. With arms extended, the weights are 1 meter from the axis of rotation, and they rotate at a rate of 0.75 radians per second. If the moment of inertia of the student plus stool is a constant 3 kilograms square meters, and the student pulls the weights to be 0.3 meters from the axis, calculate the new angular speed and calculate the change in kinetic energy. Where did this energy come from? So let's start with the concept of conservation of angular momentum. Okay, L initial equals L final. Okay, this is what we're going to use. Now we are also going to, we'll say that this is I omega initial equals I omega final. But we are also going to change our moment of inertia. Okay? Now, our givens, okay, we have that the moment of inertia of the student stool system is 3 kilogram meters squared. We will need to figure out the initial and final moment of inertia of the weights, okay, because those are going to change, right? Because the radius is changing. The mass doesn't, but the radius does. We know that the initial radius for the weights is 1 meter. The final radius for the weights is 30 centimeters or 0.3 meters. And we know that they are initially rotating at a rate of 0.75 radians per second. Okay? And we know that we need the mass of the weights. Mass of the weights is 3 kilometers. Okay, that's per weight. I believe that's all we need. Now, we have initial moment of inertia. That's done. We do not have anything else. But what we want to solve for is omega final. So let's first solve for omega final. Okay, we've got I initial omega initial equals I final omega final. So if we take I naught omega naught divided by I final, you get your omega final. Okay? But we need those values. So let's find our initial moment of inertia. Okay, we start with 3 kilogram square meters from the student in the stool, but we're now asked to find the moment of inertia of the weights as well, because that is going to be the change here. So we have 2 weights, and they both have a mass of 3 kilograms, and we are going to use the radius of 1 meter for their initial value. So what we're doing is we're taking the idea that we've got the moment of inertia of the student stool system. We're going to add 2 times the moment of inertia of the weight. Okay, now when you put that in your calculator, you will get 9 kilogram meters squared. So that is our initial moment of inertia, right? Now we want the final moment of inertia. We have still 3 kilogram meters squared. The student and the stool haven't changed, but the radius for the weights is going to change. So we start with 2 times our 3 kilograms, but now the radius of 1 meter is changing. Now it's 0.3 meters, and that is squared. Now that is going to give us a moment of inertia of 3.54 kilogram meters squared. So now we have our initial moment of inertia, our final moment of inertia, and we already have our initial angular speed. So we can actually put this in. We have 9 kilogram meters squared times, what was it, 0.75? Yeah, 0.75 seconds inverse divided by 3.54 kilogram meters squared. Okay. When you put that in your calculator, you'll find that you will get 1.91 seconds inverse, or 1.91 radians per second. Okay? So now we can see that that is a drastic increase. Okay? We started at 0.75. We ended at 1.91, over doubling our initial angular speed. Okay? And that's because the angular momentum was conserved. However, calculate the change in kinetic energy, and we need to figure out, where did this energy come from? Did we just break conservation by obeying another conservation? So let us find out. Kinetic energy in rotational world, right? Because this, we are not translating as pure rotation. This would be 1/2 I omega squared. So if we want to know the change, right, it asks for the change in kinetic energy. We want K final minus K initial. Okay. So that would be 1/2 I final omega final squared minus 1/2 I initial omega initial squared. Now remember, we need initials and finals for both because they are both changing in this scenario. So we'll factor out that 1/2. So our I final we found was 3.54. 3.54 kilogram meter squared times our final omega, which is 1.91 seconds inverse squared, minus, I guess if I'm going to use so many parentheses, there we go, minus our initial moment of inertia was 9 kilogram meters squared, times our initial angular speed, which was 0.75 seconds inverse, and then we square that as well. Okay. So our answer here is going to be something along the lines of 3.9 joules. Okay. And that is an increase, right? Yeah, that is an increase of 3.9 joules. So we gained this kinetic energy, right? If we're looking at 1/2 I omega squared, we know that our moment of inertia changed, right? It actually decreased, but that is not what's causing this increase in rotational kinetic energy. We have an omega that has over doubled itself, and that fact is now being squared, right? So it's not only just doubling, but now that relationship is being squared. That's going to overpower the change in moment of inertia, right? So we have an increase of 3.9 joules. Now, why are we having an increase in kinetic energy if our system is not doing anything, right? It's just kind of moving internally. Well, what's happening is this energy is coming from work done by the student, right? A force is being exerted over a distance. And we know, using the work kinetic energy theorem, that any work done can lead to a change in kinetic energy. So this student is doing work. That energy comes from internal energy from the student, right? So the student's, I guess it's really using calorie strength, right? It's using calorie energy to move those back and forth. And that energy just is chemical energy from eating, and that becomes the chemical energy that a person can then convert into mechanical energy, right? So as that student moves the weights in and out, that is not really breaking conservation of energy because it's all internal, but we do see that the kinetic energy has changed, right? So we didn't break the concept of conservation of energy here. What we did is we showed that work can change kinetic energy, but if the work is all within the system, it doesn't necessarily change the angular momentum. Okay? So here we can use the same concept that I demonstrated with the wheel of death, that you can change your angular speed. Even if you know enough information, you can mathematically determine what that new angular speed would be. Now, that doesn't mean that your kinetic energy is going to remain constant, right? There is going to be a change in kinetic energy, and that is because it takes work to change the moment of inertia. And as a result of changing the moment of inertia, you increase or decrease your angular speed. Right. Next problem. Keep an eye on Betelgeuse. I for moment of inertia. So after going supernova, the remains of Betelgeuse, which is a star that could supernova soon or possibly has already supernovaed. More on that in a second. The remains of Betelgeuse, which is just a stellar core, after such a massive star like a supergiant that Betelgeuse, the red supergiant, after it supernovas, all that's left behind is the core. Okay? The core is rotating with a period of 30 days and a radius of 1 times 10 to the 4th kilometers. Then it will collapse into a neutron star of similar shape. We're going to call them both spheres. It now has a new radius of 3 kilometers, so a drastic change in radius. Go from 10,000 kilometers to 3. What would be the new period of rotation of the neutron star? Hint, use ratios to simplify the solution. So first, let's introduce the idea of a period. A period is the period of time it takes to fulfill usually a cycle, right? Usually it's an orbit, a rotation, an oscillation, some kind of repeating pattern that can be measured in a period of time. So this idea is T equals 2 pi over omega. This is actually on the AP equation sheet. You can also rearrange this to show that omega is 2 pi divided by the time period. So we're going to use this concept and the concept that angular momentum is conserved, especially in space, that we can find the new period. How fast is the neutron star rotating? Heads up, they rotate really fast. So we're going to actually take that 30 days and convert it to seconds before we use it. So we are going to have a change in moment of inertia. We are going to have a change in angular speed. So they both get an initial and a final. Now, what we are solving for is period. So let's actually do some symbol algebra over here. If we take I initial times 2 pi over t initial, now we can actually solve this for our time period, okay, the time period that we want. Now, we also know that we're going to assume these are both spheres. So let's say that with that assumption, we can use 2/5 mr squared. Now, this is after the supernova, so all of the mass that is lost to an explosion, we assume has already happened. So the mass is going to stay constant. The thing that's changing here is the radius. So here we will take 2/5 mr initial squared times 2 pi over t initial equals 2/5 mr final squared times 2t over our final time period. Now, things that can cancel. There is a 2 pi on each side, a 2/5 on each side, and a mass on each side. All of those can go away because they can be divided out. So what we are left with is r naught squared over t initial equals r final squared over t final. Okay? That's how we can use those ratios to simplify this. Now, if we want t final, if you cross multiply and divide over, what you're going to get is t naught times r final squared divided by r initial squared. Okay? So we need our initial time period, which we have is 30 days. We need to convert that. Then we need the radii. We have the initial radius, 10 to the 4th kilometers. We have that. And we need the initial radius, which is just 3 kilometers. So we have all of this. We just need to convert days to seconds. So let's do that real quick. T initial is 30 days. 1 day is 24 hours. And 1 hour is 3,600 seconds. Okay. When you put that in your calculator, you get 2.592 times 10 to the 6th seconds. Okay. So we have that for our t initial. If we use all of these numbers, okay, we've got 2.592 times 10 to the 6th seconds. Now we have this ratio. Our final radius is 3 kilometers squared divided by 10 to the 4th kilometers squared. Okay. And when you put that in your calculator, you are going to get 0.233 seconds. Now, what does that mean? That means that this neutron star, instead, after the supernova, right, the core is rotating once every 30 days, right? It makes one full rotation every 30 days. After this collapse from 10,000 kilometers down to 3 kilometers, it is now fulfilling or completing one rotation every 0.233 seconds, less than a quarter of a second. That's how fast neutron stars rotate. And that's actually true. Neutron stars are very fast in their rotation. Some astrophysicists and astronomers can actually use their rotation as a clock. They can use that because they know that it's going to be relatively constant for millions of years. So they can use that as a reliable timekeeping mechanism to measure change, or maybe redshift or blue shift, and make several different measurements and compare them to that neutron star. Very interesting stuff for neutron stars. So that's how we can use time period to measure the new rotation, right? So time period now introduced. Now, number 2, this is more discussion, but Betelgeuse is over 640 light years away and will likely supernova in the next 50 years if it hasn't already. Now, would the radiation from the supernova be enough to wipe out life on Earth? So there is that concern that if a star supernovas near our solar system, it can release gamma radiation, maybe possibly a gamma ray burst, but I don't think so. The radiation could just destroy all life on Earth. Betelgeuse will not do that. Okay, for a supernova to be lethal to life on Earth, it needs to be within 50 light years, and there is no star within 50 light years capable of a supernova that could kill us. So we are safe from supernovas for the time being. Now, how long will it take the radiation to reach us after the supernova? So it's not a matter of if, it's a matter of when Betelgeuse supernovas and when we can see it. So when it's talking about radiation here, it's talking about electromagnetic radiation. That electromagnetic radiation is simply light. When Betelgeuse supernovas, it will take 640 light years. That's how far the light's going to travel, right? It'll take 640 light year trip from the supernova to us. Now, traveling through space, it will travel through a vacuum, meaning it is capable of traveling at the speed of light for that trip. And since it is traveling 640 light years, we know that it would take 640 years for that supernova's light to reach us. Okay? So if we think that we'll be able to see Betelgeuse supernova in the next 50 years, that means that those scientists that made that prediction believe that it has likely already exploded, and we're just waiting for that information light to reach us. Letter C, last part, how bright would it be during the daytime? So a lot of people are really interested about this, myself included, because a supernova of this magnitude is possibly visible during our daytime. So you'd actually see not just the sun up, but you could also see a star in the daytime sky. Some scientists have said that there is a 20 to 50% chance that any Milky Way supernova is actually visible to the naked eye and possibly visible during the daytime. So Betelgeuse supernova, really interesting, and it's coming. Now, next problem, hanging out on a merry-go-round. Merry-go-round is slowly spinning counterclockwise as shown. You can see the arrow right there, counterclockwise as shown. What happens to the angular speed of the merry-go-round if the person A starts walking clockwise on the rim, B starts walking counterclockwise on the rim, C starts walking to the center, or D launches a ball southeast from the shown position? So this is going to kind of segue into our next concept, which is going to be conservation in a collision. However, as that person starts walking clockwise on the rim, okay, that would cause the wheel to move counterclockwise, right? That is due to conservation. If If that person, look, I believe that's a girl. Yeah, it's a girl. If that girl starts walking clockwise, that means that her feet have to be kicking backwards, right? We've talked about the Newton's third law interaction of walking, right? You actually don't move yourself, right? You are actually result of a third law pair when you walk. You are actually kicking off the ground ever so softly if you're walking, but you are kicking off the ground and the ground kicks you back. And that is why you actually walk. Now, if you are unsuccessful at walking, that is probably because there is no static friction to push you back. Static friction is what's going to propel you forward. If there is no static friction, for example, it's slippery, or you are Michael Jackson and are moonwalking, right? Moonwalking, not really a trick of friction, right? But if there's no friction, then you just stay completely stationary, right? However, if she is walking clockwise, that means that she is going to kick the wheel counterclockwise, okay? And then vice versa on part B. If the girl starts walking counterclockwise, then the wheel will actually feel a force to start moving clockwise, okay? So wherever the person wants to walk around the rim, the merry-go-round will actually go the opposite direction to conserve angular momentum. Part C says, what if the person starts walking to the center? So that's interesting. And that's a very similar concept of what we've already talked about. If angular momentum is going to be conserved, okay, we have the same idea that if this person starts walking towards the center, there is this mass on the object that is now decreasing its radius, which means that you're going to decrease your moment of inertia and increase your angular speed. Okay. Now, if the person launches a ball southeast from their shown position, okay, that shows that we are actually going to start moving. So the wheel would continue to move counterclockwise. Now, you can think of this force, right? This one's tough, right? So think of the linear momentum exchange when you push a ball, right? When you throw a ball, the force that you exert on the ball is exerted on you as well, right? So that's a recoil concept, recoil conservation. So when she pushes this ball through the air, she is pushed in the opposite direction. But since this is pushed southeast from her position, southeast. I'm thinking southwest. So if she launches this ball southeast, okay, that means that the resulting force on her body would be this way. And assuming that the friction holds up, and when she is pushed, there is also a force on her feet that pushes the merry-go-round in that way, then you get a net torque, and that net torque is going to cause motion in the counterclockwise direction. Okay. Now, if she were to throw it southwest, like I was misreading, if she throws this ball southwest, there is absolutely no change in angular momentum. And that is because as she throws it, she experiences a recoil in this direction. But both of those arrows are parallel to the axis of rotation. So remember that torque, okay, being R cross F, those need to be perpendicular to maximize their efficiency. If R and F are parallel, that means that there is absolutely no torque. So if she threw it at the axis of rotation, right, throwing it southwest across the axis, then there's no change. Throwing it southeast, now you start going the opposite way. If she were to throw it northwest, then it would have the opposite effect. Throwing it northwest would result in a southeast force exerted from that recoil, which means that she is pushed southeast, and that would encourage clockwise motion. So that's how conservation of angular momentum can actually be helped, assuming this is all frictionless. Okay? So this is how this is going to work on a merry-go-round and encourage this rotational motion. All right, so our last question for this video. Conservation of angular momentum in a space station. So a space station has a radius of 100 meters and a moment of inertia of 5 times 10 to the 8th kilograms square meters. It's a lot of moment of inertia. The station is rotated to maintain an acceleration of 1g along the rim. A crew of 100, average mass of 65 kilograms, live on the ship at the rim. When 100 of the crew go to the axis for a meeting, the angular speed changes. What acceleration is felt by the remaining crew at the rim during the meeting? So let's get our givens. First, we know that the radius is 100 meters. The moment of inertia of the ship is 5 times 10 to the 8th kilogram meters squared. The radial acceleration is 9.81 meters per second squared. The initial mass is 65 kilograms times 150 people. That gives you, 9,750. 9,750 kilograms. Then the final mass of those people, we are now only considering 50 of them because 100 of them are on the axis of rotation. So that means that they are not going to contribute to the moment of inertia. Right, now, if we look at this through the lens of conservation of angular momentum, okay, we know that the change of moment of inertia is what's going to change our angular speed, right? So we need to find out what is the initial and final moment of inertia. So here we're going to take the moment of inertia of the ship plus the mass of the crew times the radius of the crew. So here we have 5 times 10 to the 8th plus, what do we have? Initially, we have 9,750 kilograms times 100 meters squared. So this will give us 5.975 times 10 to the 8th kilograms square meters. And that's for the initial, right? Now, 100 of those people are going to go to the axis, and we are going to lose their mass to consider for the moment of inertia. So that would be 5 times 10 to the 8th plus 3,250 kilograms, again, times 100 meters squared. And that will give us 5.325 times 10 to the 8th kilogram square meter. Now we need our omega, right? We don't actually know how fast it's rotating. We know what its acceleration is, right? We know that it's got a radial or centripetal acceleration of 1g, which would be 9.81 meters per second squared. We also know that that is omega squared r, right? From our rotational days, we know that the centripetal acceleration is equal to omega squared r, or v squared divided by r. So if we want our initial omega, we will take the square root of ar divided by r, which would be the square root of 9.81 divided by 100. And that would be 0.313 inverse seconds. Okay? So we have everything we need, right, to solve for omega final. Using this equation up here, right, I am going to say that omega final is initial moment of inertia times the initial angular velocity divided by the final moment of inertia. Okay? So we have 5.975 times 10 to the 8th times 0.313, all divided by 5.325 times 10 to the 8th. And when I put that in my calculator, I get 0.351 inverse seconds, but that's not the end of the problem, right? That tells us the radians per second on the spin, but we want to know what is the acceleration. So let's take that omega and square it. So we get 0.351 what did I say? 351 seconds inverse squared times 100 meters. And you're going to come up with 12.3 meters per second squared, which is pretty tough. That means that every time this 100-person meeting happens, the rest of the crew is going to suffer a 25% increase in gravity, which is going to be brutal. Okay. All right, so that's our video on conservation of angular momentum. We're going to continue on in our next video to talk about the conservation of angular momentum in a collision.